Recording in progress.
So thank you everyone for coming to today's HICE. And today we are having the introduction. Join me to welcome him to give the speech on extreme precise RV, the road to 10 centimeters per second.
Good, thanks. So very happy to be here. Yeah, so it's been a great time. Came with my wife and we are having a good time in Tucson. This time of the year is great.
Yeah,
lots of things to do. And of course, happy to talk about other things I have been doing over the past few years. Feel free to interrupt at any time. I have to confess, I took something that was more or less on my hard disk. I added a few things that I thought might be of interest. Yeah, so feel free to interrupt at any time. Okay, yes, so radial velocities is one of the well-established methods. Of course, was the first method to actually do extrasolar planets around main sequence stars. One specific point that may be interesting for this group that works on high contrast imaging is what does that mean in the context of, say, missions like Habitable Worlds Observatory, which will characterize atmospheres of potentially habitable planets. So planet mass is a very important aspect of habitability because the surface gravity sets the scale height for the atmosphere. The combination of mass and radius gives the bulk density and therefore a clue to the interior composition, which is of course also relevant for habitability because it determines outgassing and things like that. To get dynamical masses, we know of two methods. One is radial velocity, the other one is astrometry. So I'll talk about radial velocities today. Astrometry really means you have to go to space and do actually about 2 orders of magnitude better in precision than what Gaia has been doing. So there was an astrometry mission in the plans by NASA. Actually, they started building it, the Space Interferometry mission, but that was then abandoned about a decade ago essentially because JWST was so expensive, nothing else fit into the budget. So in principle, also radial velocities and astrometry can identify targets for chronographic missions. So if you have the knowledge that there is a planet that you found with radial velocities, you know to which star to point your observatory. So that increases the mission efficiency. Also, it can provide early guidance in your design choices. You know how many Earth-like planets there are, around which stars there are. The earlier you know about that, the better. But to be useful in this context of habitable planets, you need a precision of better than 10 centimeters per second. So, talking about the road to 10 centimeters per second, it's straight and it's short. So, what's the problem? And I come back to the problems. Yeah, how? And so, first thing are a few rough numbers and scaling relations. So this is my one-page cheat sheet on numbers on extrasolar planets, which is some numbers that are very useful to remember for anybody who still has to pass some exams, or people who want to ask questions in exams, or people who just want to do rough calculations. So the first thing to remember is the radii of the Sun to Jupiter to Earth. The relation is 100 to 10 to 1. So this is really easy to remember, and this is extremely useful. Also, the densities are about 1 to 1 to 3. Jupiter and Sun have roughly the same density. Earth is 3 times denser. So at the same density, now the masses would just scale with a cube of the radius. But because of this density ratio, the mass ratio is 300,000 to 300 to 1. So these numbers are actually accurate to a few percent. Pretty good. And very easy to remember. And so then also, if you know the orbital velocity of the Earth, which is 30 kilometers per second, and you remember the scaling of the Kepler velocity, the velocity is proportional to 1 divided by the root of the semi-major axis. And the definition, 1 AU at 1 parsec is 1 arc second. Then you can, it's very straightforward to calculate things like Earth around a G star at 10 parsecs. The velocity is just the velocity of the Earth times the mass ratio. So 30 kilometers per second divided by 300,000 is 10 centimeters per second. Or the semi-major axis is 0.3 of the motion of the sun is 0.3 microarcseconds as seen from 10 parsecs. And so with these numbers that really are absolutely straightforward to remember, one can do these calculations very, very quickly. That's very useful to remember. So if you look historically at advances in radial velocity precision, 1995 was the first detection of an Earth-like planet around a main sequence star, for which Michel Mayor, Didier Queloz got the Nobel Prize. That was a precision, or the amplitude of that motion. Actually, the precision was higher. The amplitude of that motion was about 50 meters per second. And over time, until roughly 2010, we see that it got better and better and better, and planets with smaller and smaller amplitudes were discovered. And then starting in the early 2010s, the precision didn't increase very much anymore, or the velocity amplitudes of the newly discovered planets remained at this level of about 1 meter per second. So the question is why, and what can we do to get better than that? So we have to look at error budgets. And of course, this is all in the time domain. So then we have error sources. There are error sources with periodic terms. There are daily, annual variations due to observing conditions, for instance. There are cooling cycles and so on. So we have potentially periodic signals in our data, in our time series. There are also some with characteristic timescales, but not periodic. Stellar activity, sampling of the time series, maintenance cycles for instruments, jumps. They have a characteristic timescale, so it's not white noise. There are red noise terms, drifts, aging. And so the first thing is, if you want to construct an error budget for our RVs, it's actually quite complicated because of these different kinds of time dependencies. How do we separate these on different time scales? Should we actually work with power spectral density distributions rather than a single specification like 10 centimeters per second? What actually does that mean over a certain time scale with periodic signals? Not so. There's some difficulty already in formulating exactly what you want. And then there's kind of fine-tuning of your science requirements. If you have a requirement and set it to be able to detect the exact Earth analogon, it will have a period of exactly 1 year. And so have a terrible aliasing problem if you have ground-based observations. Because by definition, you can always observe part of the orbit, and then it's a daytime object. And when your nighttime season starts again, you are re-observing the same part of the orbit. So it can be very different on whether you set your requirement for 0.8 years or for 1 year because of these issues. So this would radial velocities measurements fundamental are differential measurements, and we do very highly differential. First of all, we measure always wavelengths or frequencies relative to a calibration source. We do not observe absolute velocities. We observe relative to a calibration source. Then we do time differential measurements. We are not really interested in things that are static on the star, that do not change over time. We do not normally need an absolute radial velocity. And so, for instance, in cross-correlation methods, this is kind of explicit. We take standard, we cross-correlate against that radial velocity standard spectrum, and then we do time differential measurements of the RV. This is all complicated by the time variable barycentric correction. I mean, the Earth moves around the sun at 30 kilometers per second. So unfortunately, it would have a much easier task if we had the spectrum stable on the detector, but we don't. The spectrum moves by plus minus typically 10 kilometers per second in the course of a year. So we have to take that out. And actually, we have this big 10 kilometer per second sine curve superimposed on the signal of, or a 10 centimeter per second signal that we want to detect, superimposed on a 10 kilometer per second sine curve that we can compute very exactly. Yeah, ephemerides are very, very precise, but all kinds of systematic effects that can be introduced by sweeping across the detector. So that we have to keep in mind. So the barycentric correction, although one can compute it very precisely, is really a fundamental complication that is quite important technically. So, and then there are complications in this differential nature that also enter the error budget. So sometimes people split this into calibratable or non-calibratable effects. And then the question is, how do you quantify calibratable? Now, for instance, when you build a spectrograph, you can do a finite element analysis of how stable things are. And the FE analysis works pretty well. But if you rely on, say, a differential measurement where you put in a calibration signal and your measurement signal, you want to know the differential drift between the two. This is very, very difficult to model. So they may drift a lot, and you can model that. But how much difference is in the two drifts, that is much, much harder to predict. So, and then the question is verification strategies. How do we measure success? There are typically different verification processes. So people who build instruments know you do verification by inspection, by demonstration, by analysis, by testing, end-to-end verification. End-to-end verification can also be quite difficult. Yeah? When you build your instrument, you put it on sky, then you get data, and the data are all over the place. You wanted precision X, and you get precision 10 times X. Why is that? How do I reverse engineer from my data to get information about my instrument back? So you try, of course, to do this with subsystems, but these verification processes by themselves need thinking through, and I'm pretty sure this is true in all types of instruments. If you have wavefront errors in your system, where does the wavefront error come from? It's not so easy to tell that from your sensor data. So, talking about challenges in RV. The first challenge is basic physics. And the basic physics, of course, is the photon noise limit. And the photon noise limit basically is given by some constant. Then you divide by a quality factor that measures the information content in spectra, and then by the square root of the number of photons that you receive. So in radial velocities, it's important to take this factor Q into account that measures the information content in spectra. Unlike most other techniques, where you are mostly interested in the number of photons that you receive, and the number of photons determine how well you can center something. Yeah, if you take your image, whether adaptive optics or direct imaging or what, if you want to kind of compute the centroid, it gets better if you have more photons in it. Here it's also the case, there's this square root of n factor, but also if you have a flat spectrum, you have no radial velocity information in it. You need sharp absorption lines. So this means, first of all, there's a dependence on the spectral resolution of your spectrograph. If you don't resolve the lines, you don't get the information. And also, there is a dependence on the rotation rate of the star. And the spectral type. The spectral type determines how many lines you have, and the rotation rate of the star determines how broad the lines are. So typically, we work at spectral resolution of 100,000, which is matched to the width of lines, say, in the sun. The metal lines in the sun are a couple of kilometers per second, and this is why a stellar spectrograph, almost by definition, has a resolution of within a factor of 2 or so. It's 100,000, because that extracts the information that is there in a spectrum of a cool, slowly rotating star. It also means that if you have more stars with higher rotation rates, like young stars, earlier spectral types, radial velocities don't work very well. So what's desired is the high resolution, large wavelength range, and then the spectrograph design typically is cross-dispersed shell spectrographs. So what do you know what a cross-dispersed shell is?
Not to the cross-dispersed part.
Okay. And a shell spectrograph works at high spectral order,
Yeah.
at high resolution, and then you get the orders overlap. Yeah, 1 micron in, say, the 100th order or the 1 micron at the 101st order would be the same location on the detector as 1.01 micron at the 100th order.
Okay,
Yeah, they land on the same place on a detector. And then what you do is in your beam, you put in a second dispersing element that is dispersing in the other direction.
Okay.
Yeah, and this is what it calls cross-dispersed. This has low dispersion. So the 2 spectral orders get separated in the other direction. You get a 2D detector image where you have individual orders. I'll have a picture a little later. Yeah? But this is the universally adopted design for radial velocity observations.
Do you still couple data between the different cross-dispersed orders, or do you mostly try and treat them independently?
So do we
Like when you cross-disperse the data, right? So you have the multiple orders, yeah. I mean, do you generally treat them as a series and like analyze them together, or do you often treat them individually?
We normally do the analysis on an order by order basis.
Yeah.
We generate data products that are stitched for people to take a quick look, or for people to do, say, stellar astrophysics with a spectra. That is a bit handier. But for the precision analysis, we do not normally add them together and stitch.
Yeah.
We do order by order, compute a radial velocity for each order, and then do appropriate averages.
And that's just due to basically all the different errors in chromaticity, I guess, that wavelength effects, like just.
Yeah, I mean, you have to deal with resampling and noise weighted averaging and things like that are just it doesn't help you, and it complicates things. And there's information also in doing this order by order, because you get the difference between the different order, or the orders tell you something about your error bars and things like that. So there are benefits, and there's not much to be gained by putting it together. And the other thing is because of this rule, and of course you want an efficient instrument. But a shell spectrographs typically have 5 to 10%. So I think we never get to 10%, obviously. So that is a big drawback also. We are spreading the light over very many pixels, and we have typically low efficiencies, and therefore we need a lot of glass.
Is that number including the atmosphere as well?
So 5% would be including the atmosphere. Yeah, and yeah.
Okay.
But the gratings are the biggest losses, for instance.
Sorry, the what?
The grating.
The grading.
The gratings. Yep. So here's an example for this quality factor, and here so we see on the top the curves with these are non-rotating stars. So the quality, there's quite a bit of information, but it depends on the spectral type because the K stars have more lines than the F stars. So that's the number of lines in the spectrum effect. And then the bottom curves have a higher rotation rate, a V sin I of 10 kilometers per second. So that means the lines are smeared out. And that means there's a loss of information in the spectrum. And one can also see now that these curves flatten out to the right. So once you are resolving the lines, there's nothing more to be gained. Yeah, that is just Nyquist tells you if you have a certain number of samples per resolution element, you can't improve things anymore by going to higher spectral resolution. But for a G star, typically we would still be gaining by going beyond 100,000. So 1 times 10 to the 5 is in the center. So this is our typically 100,000 spectrograph. This is a good compromise between going as far to the right as we can to climb up on these curves to get a high information content out of our spectra, versus things get more expensive, things get bigger, things get less efficient when you try to climb up. So most people end up between 80,000 and 120,000, somewhere in this range, building that for the spectrograph resolution. So that's basic physics, just photo noise calculations, information content of spectra calculations. That is the best we can ever do with an ideal instrument. So challenge 2 is build a stable spectrograph. First of all, stable pressure means vacuum system. We all build spectrographs in vacuum systems. Thermal and mechanical stability means typically we have tolerances of about 10 millikelvin for our temperature control.
Sort of the whole bench too?
Ideally the whole bench, yes. There's choice of materials, and so there are discussions, and different groups have adopted different things depending on budgets, whether nobody can afford INVAR, but the Keck spectrograph, the new one, has actually a zero-door bench. Most people use aluminum benches. So mechanical thermal design is really important. No moving parts. So this is my mantra. No single moving part in the vacuum vessel, because anything that moves introduces disturbances. This is much less critical for the iodine cell method, but that has other limitations. I come back to that in the talk a little bit about calibration. Yeah, there are different calibration strategies. The Keck-HIRES, for instance, that was used a lot, and on the LIC spectrograph that was used a lot in the early days, in the starting in even before 1995 into the 2000s. For many of the planet detections, they used an iodine absorption cell to calibrate the wavelengths. I come back to that, and that has less limitations. So this is still a method that can be used very nicely if you have a small and inexpensive instrument that you want to use at a smaller telescope, for instance. That is your method of choice, because then you can get around of some of these limitations. Of course, there are tons of detector issues. Detectors are always an issue. So spatially non-uniform response, pixel-to-pixel variations, so flat fielding, intrapixel QE variations. Those can be a headache. One specific thing that has haunted some groups is a non-uniform pixel grid. So depending on how your CCD was manufactured, there may be a lithographic mask that exposes part of the CCD and creates a nice regular pixel grid, but not for the whole chip. And it is offset, and the next 128 by 128 pixels are come through the lithographic mask, and that is moved again. And each one of these steps at the boundary, you get a pixel that is a little bit bigger or a little bit smaller than the other pixels. So your pixel spacing has, if you put it or the number of pixels and assign the microns on the chip, there are jumps in this. Also, what is problematic for us is, so
would that not be fixed with just the sort of flat fielding part of the corrections?
it's not just flat fielding. The flat fielding is a single pixel, but that single pixel, gets more or less photons, and that is the flat fielding effect. But the other effect is that if you have, say, you want to calibrate your pixel in wavelength space, so you have calibration lines, and then you assume that you have a linear interpolation between these, and each pixel corresponds, or the number of pixels is a linear function. The wavelength is a linear function of pixel number.
Yeah.
And it's not linear at this point, it jumps. Yeah. Because the pixel was bigger.
Yeah.
There were bigger wavelength range. Yeah, and that information I should have perhaps have given.
Yeah.
Typically 1 meter per second corresponds to 1 millipixel. So our spectrograph resolution is 100,000, so that's 3 kilometers per second per resolution element. If you do 3 times oversampling, you have pixels corresponding to 1 kilometer per second. Each pixel is 1 kilometer per second in velocity. So a precision of 1 meter per second is a precision of the thousandths of a pixel. Yeah, or in other words, 50 nanometers or 10 silicon atoms. Yeah, so so we are interested in these effects on the scale of a thousandth of a pixel.
Okay.
Yeah, this is why these things matter. I should have said that at the beginning. Yeah, and also the spectrograph stability. Yeah, if you shift everything by tens of nanometers, you have already exceeded your error budget. And this is why we may have to measure differentially.
Okay.
Yeah, also on detectors, what can be very problematic is non-perfect charge transfer efficiency. On a CCD, you move the charges through the pixels. So this is not 100% effective. There's always a little bit of a trail. Yeah, one electron in 1 to the 6 or 1 to the 7 is left behind. And that charge transfer inefficiency depends on the number of electrons in that pixel, which means that the point spread function on the detector or the line spread function becomes dependent on the intensity. Yeah, so if you have, so if you have a little if you have two exposures and the exposure levels are not exactly the same, you leave a few more electrons behind, and that of course shifts the centroid of your function. And that can be enough to introduce noticeable errors.
This is all just stuff we never have to worry about.
Ruben worries about it constantly.
Oh,
Oh yeah, there's a whole bunch of other ones too.
There are variations of
There's-
that matter for astrometry, variations that matter for deep imaging. There are some things that are very specific to radial velocities, but these are of course detector effects that other people also worry about. Nonlinearities, of course. Then amplifier glow and heat generation, which warps or extends part of the detector. And of course, this is different and less known for near IR detectors. Yeah, a lot of the spectrographs work in the visible wavelength range with CCDs. But there are also now, the instrument that I am involved with also has a near infrared channel. And there, of course, we are using now Y detectors, and they are different beasts altogether. And many of these things are much worse and less understood. And everybody is worried also that maybe in the future we will not be able to get CCDs anymore. At some point, all of astronomy may be forced to switch to CMOS because nobody's will make affordable CCD detectors anymore. So what happens if you have to go CMOS? Nobody really knows.
Yeah, we're doing a lot of CMOS, and one of the things we're seeing is a lot. And we haven't done enough with CCDs for in this scenario to see if the problem. We see photoelectrons leaking from pixel to pixel, so it's sort of your CTE problem.
Yeah.
But it shows up as signal in the next pixel.
Yes.
And then it washes out the high contrast region because it creates this smear.
Okay. Oh, yeah.
You have a speckle, it has a PSF, but then it actually has a photoelectron smear that's very broad.
So optically, you dig a deep.
Part in 1,000.
Optically, you dig a deep hole, and then the detector fills it again.
Yeah, and we can swap detectors and see that it's a detector effect.
Yeah.
But we don't know why.
Good. So once you have dealt with these, you also have to make sure that the light coupling into your spectrograph is stable. So you have to go from the telescope into your spectrograph. And of course, the point spread function on the sky depends on the seeing, and is also wavelength dependent. And you have telescope guiding errors, which again depend on seeing, on brightness, on sky position. You have atmospheric dispersion that gets corrected with atmospheric dispersion corrector to a certain degree, imperfect. And what is absolutely necessary for us is to do fiber coupling to achieve the stability that we need. Because if you have a slit coupled spectrograph, you just put classical design, you put your spectrograph at the telescope, there's a slit, you image on the slit. Of course, what the spectrograph does, it re-images in monochromatic light. The spectrograph re-images the slit onto the detector. And then if you have any instability in the input, of course, the output also moves around, and that looks like a wavelength change. And because we are interested in thousands of a pixel, that means we would have to stabilize everything to thousands of the slit width or something like that. It's impossible. Anybody doing AO knows. Stabilize something on the ground to thousands of a pixel tip tilt is not going to happen. Yeah. So the nice thing about fibers is fibers provide scrambling. Which means the output of a fiber is much more stable than the input. Because there are these many internal reflections that mixes up the light that you put in. However, not completely, because if you think about it in geometric optics, If you take a fiber as a light guide in geometric optics, the angle at which things are reflected, light is reflected, remains constant. And that means a fiber with a circular cross-section does have very good scrambling properties in the azimuthal direction, but not in the radial detection. If you have a circular fiber, a multi-mode fiber, and you illuminate it, say, with a single mode fiber on the input, you have an input spot, the output you will have a circle more or less. And so to overcome that and to also good scrambling in the radial detection, either we have some external scramblers where we exchange, say, pupil plane, the focal plane, or play other tricks to mix the light, or we use non-circular fibers. Yeah, so I mentioned that at each wavelength, the spectrograph images the slit. Image motion looks like RV variations, and then the fiber coupling provides the scrambling. The output is more stable than the input, and more intelligent or more sophisticated fibers actually help. So this is from when we built an instrument a few years ago. I had a graduate student who looked at this in very much detail. So here's this, what I described, a round fiber, and you have the fiber input on the top. You move a small light source on the, inject the fiber, and then we have the near field and far field coming out of the fiber, and you have these rings. And if you do that with an octagonal fiber, it looks much better. So this is one of the tricks that we play is we have a 1 or 2 meter section of octagonal fiber in our coupling, and that provides very nice light scrambling and makes the output very uniform, because the octagonal fiber doesn't have that symmetry that the reflection angle is conserved.
Yeah, but you lose throughput or something? There's always a disadvantage. What's the
No,
disadvantage?
you lose virtually nothing in
Right.
throughput. You can actually couple an octagonal fiber to a round fiber. They are so similar that if you do in the couple percent range that you lose, and the fiber itself is as good as a round fiber, and it's just if you think about it as a Julian who did this PhD thesis actually did an analysis of optimal cross sections, and to first order you can think about it as a billiard, and if you have ever taken a class on chaos theory and heard about ergodicity in billiards, you want an ergodic billiard, and the octagonal fiber is such an example, and round is not ergodic because you conserve the reflection angle. So that's the big difference in the cross section.
One thing that people often look at for high contrast imaging is using single mode fibers to couple the starlight and project the speckles. So could you do single mode fibers in your focal plane and then put the hexagonal fiber behind that to scramble? Would that be a way to delay?
Yeah, so that's another good point. The question about, say, speckles that you get out of your fiber. And there are two choices. One is indeed single mode, and that is normally limited by the fact that at the wavelengths we are interested in, which if you look at this quality factor that we discussed before, about if you look at that for G stars, most of the information actually is in the blue part of the spectrum. So you want wavelengths typically between 3,800 and 5,000 angstroms, and your AO system, even for a very bright star, will not give you very high trail in that wavelength range. So single mode is applicable in the near IR. And now there are a number of spectrographs that are being developed. Single mode spectrographs. There's one for at Palomar, there's one for Keck. The LBT has an instrument that will come soon called iLocator. That these are infrared single mode designs. And the other choice is and then multimode fibers, which is everybody else is using multimode fibers. And there indeed you have to watch out to have a sufficient number of modes that you kind of average over the speckles in a reasonable way, or we actually try also to randomize by having devices that systematically bend the fibers so that we mix up the speckle patterns and average over speckle patterns. Yeah.
Need, or whatever it is, a Keck, they have these like big arms that like shake the
Yeah.
fibers like this. Is pretty funny.
Yeah. So you want to do it gently, not to break. I mean, if you don't want to, actually, you wouldn't really want to agitate a fiber for years. But
This sounds stressful.
yeah, stressful is exactly the right word. Yes. On the other hand, yeah, to average over and make sure you don't have any static speckle patterns. Yeah.
Afraid I have to, but thank you. This is
Good.
great.
Yeah. Okay. So then you have to have stable and precise calibration. And so there are two different approaches. One is, I talked about this iodine cells, absorption lines that are superimposed on a stellar spectrum. Very early on, people used telluric lines, so the atmosphere. And of course, that is limited because the atmosphere is not that stable. Yeah, there's wind, and so if you look upwind or downwind, it gives you tens of meters per second shifts in the telluric lines. But then there's this technique that was developed by Jeff Marcy and Paul Butler at Lick with an iodine cell. So you put an iodine as an absorber into your beam, and that means that you take one spectrum and it contains both the calibration information and the stellar spectrum. And there's the other technique that almost all other instruments use, and that is you have a separate emission line spectrum. So there you have two fibers feeding the spectrograph, and that is the normal approach taken, that you have two spectra, and one carries the calibration light and the other one carries the stellar light. You can combine both techniques. There are big differences in the system design and in the data products between these two calibration approaches. So if you have an emission spectrum, you can have large wavelength coverage. Yeah, the absorption spectrum is always only a limited wavelength range, namely where the absorption lines are. Here in the emission spectrum, you can pick your calibration source to cover whatever wavelength range you need. It's high efficiency. You're flexible in what the emission line source is. The data reduction is relatively straightforward, relatively speaking, to the other. The spectra are not contaminated, but you need this very high spectrograph coupling and coupling efficiency, and therefore expensive and specialized instruments. And that's what basically what I explained before. Everything has to be extremely stable. So this is what an example, yeah. Here you have simultaneous exposure. There's the stellar spectrum. These are the lines with the traces with the absorption lines. This is the stellar spectrum. You see, we have an image slicer in the instrument, so we cut the image of a star into two pieces. If they don't put them on top of each other, that gains spectral resolution. Therefore, this is slightly weird double trace, and then the emission lines are from emission line lamp. Yeah, and what we want to measure is we want to measure the shift between the calibration and the stellar spectrum with a precision of 1,000th of a pixel.
So if your emission line spectrum is like, you have picked your source, they're probably lamps or something.
Yeah, it's a lamp.
So this then comes down to how well you can align the two spectra. Doesn't that then end up just depending on your whatever absorption lines are in your stellar spectrum that you're using to align the spectra then, or is there something else?
Well, you use this calibration spectrum to determine any drifts of the detector, for instance. Yeah, if you see that these drift on the detector, you assume that this one drifts in the same way.
Okay.
Yeah, so this takes out your instrumental effects.
So you just apply basically how your wavelength versus number of pixels, and then you
Yes.
just shift. You don't match the two spectra.
No, there's no matching. In
Okay,
that
okay.
sense. Yeah,
Okay.
but it's kind of the ruler against which you measure your wavelengths.
Okay.
Yeah, now there are different types of sources that you can use for the calibration lines. One is emission line lamps, like this one. So they are available for most of the relevant wavelength regimes, relatively inexpensive. They have a long heritage, but they have very uneven wavelength coverage. As you saw, it's not regular. Uneven line brightness and saturation of the brightest lines, that can be a big problem. You want to have many of the not so bright lines to have a lot of calibration information, but then the very brightest lines can really swamp your detector. Aging affects long-term stability. So these are age, and then when they age, the line ratios become different, and when you have line blends, then one of the lines in the blend can become stronger relative to the other, which leads to an effective shift in the wavelength and stuff like that. So aging is a problem, and we have increasing quality problems that is mostly affecting thorium lamps. It's a real problem now to get good quality thorium lamps.
Sorry, just so you know, I think we have to leave in 5 minutes.
Okay, good. See how much I can do. So these are the bright lines. Then there are Fabry-Perot etalons, nice large wavelengths for calibration with each line spacings, but they are not absolute standards. There's no atomic standard behind the Fabry-Perot. So you need external stabilization, calibration. They're sensitive to dispersion effects. So here, nice small device, but you need some external calibration for that. So now there are laser frequency comps, extremely stable over long periods, equal line spacing, equal brightness. There's been rapid development in laser frequency comps, but they are still very expensive. You cannot really operate them in a hands-off way. And they are highly coherent, so you need to suppress also modal noise. So because we have multi.
I also know the one at Keck at least takes also just like a huge amount of actual physical space in the basement.
Yeah, so laser frequency comms look good at first sight, but they also have their operational problems. So then there's data reduction. Okay, I go through this quickly. And then the real big problem are unstable stars. The stars are not stable, yeah? There are variability on the stellar surfaces. Star spots, oscillations, convection, granulation, activity, magnetic cycles, all the interesting stellar astrophysics with timescales from minutes to years. And the primary effect is on the line profiles. And this is usually wavelength dependent. Yeah, for instance, if you have a spot and the star rotates, the spot is when first on the side that is blue shifted. So if there's a spot that takes away light, you get an effective redshift of your line. And then it moves across the surface, and later you can push it and so on. And this is the ultimate physical limit for RV planet detection. So that's the biggest worry at the moment, and that may be a real roadblock that cannot be removed.
And what in centimeters per second? I mean, it depends on the star, obviously, but
yeah, so this is
sun-like star.
Yeah, so on the sun, the effects are on short time scales of a couple of meters per second. And I think we don't even know very well how stable it is over a solar cycle. And so the quietest stars have about a meter per second or so RV variations. And so there are now lots of people looking at different techniques to mitigate these.
But presumably, there's some limit that can only average down
Yeah.
so much,
Yeah.
right?
Yeah. So some analysis techniques are just trying to average down, but that's probably not quite sufficient. There are all these, there's a long list of physical effects. Here are solar RVs for 3 years.
Yeah.
So the dispersion is on the meter per second level, and in the periodogram, of course, you see the 1 day, which is more of a sampling issue, but then you see the rotation period of the sun and things like that. If you go to even shorter timescales, you get the P-mode oscillations. Also, if you take the sun as a benchmark, several meters per second. So the brute force averaging really doesn't work. And I would think that Jupiter, the RV signal of Jupiter and the 11-year solar cycle, they could be very hard to distinguish. And we don't understand it. Yeah, even if you take integrated images of the sun from space and try to predict from the images of star spots and so on what the present RV is, you can't do it to this level. And we also know that the sun may be less active than the typical sun-like star.
Yeah, sure.
It's one of the lessons learned from Kepler. And extrapolation is difficult. Okay, and then the last challenge is our atmosphere. So there's telluric absorption that adds noise. It's very strong, especially in the red and in the IR. So especially if you want to look at cool stars, then that becomes a problem. Depends on air mass, humidity, winds. You may have to mask lines. You may have to model weaker lines. So depending on where you are in wavelength range. So then I'll leave this as kind of the summary slide, which hopefully matches your schedule. The 7 big challenges are the basic physics of photo noise, which I put in light color here because it is at least well understood. You know what you are dealing with. And stable spectral graphs is technical issues, but we know basically what to do to push into this regime of about 10 centimeters per second. Coupling can be more difficult. Calibration and data reduction have certainly issues that are difficult to deal with. Number 7, the atmosphere. I think we need more work on this, especially in the IR and in the red. But the real big problem is the unstable stars. And my take on it is we really have to kind of change the paradigm and come to an observing strategy in which we say, well, we do not measure radial velocity, then we apply corrections based on what we think the star is doing. But from the very beginning, we must have a goal of measuring both the kind of state of the surface of the star and the radial velocity in one combined measurement, and use all the information that we have in the spectrum. And we have spectral, the shapes of the spectral lines and line ratios and all these things to work out and extract explicitly information on the star and analyze that together with the RVs to get down into this regime. And that's the big challenge. If we can't get there, then we will probably never get the mass of an Earth-like planet around a G-type star.
Interesting. Sounds hard. So are there data sets now that have enough, like, I mean, are you saying using the data that's just in the spectral data itself, or are you thinking supplemental data being like, I don't know,
Yeah,
a different telescope looking at it with a different instrument at the same time?
The high resolution spectrograph, of course, gives you a lot more information than, say, photometry.
Sure.
You can think about other things like polarimetry or even spatially resolved, which means interferometric spectroscopy. But typically, I would think you have to try to extract. That is the first order. The first thing that you should try to do is extract all the information that is in this enormously information-rich cross-dispersed shell spectrum to learn about what the star is doing.
So it's like turning into a huge forward modeling problem in some ways.
Yeah, and well, we can think about it. I start to think about it as a dimensionality reduction problem.
Right.
We have this shell spectrum and normally reduce it to one number, which is RV. But we should not reduce it to one number, but we should reduce it to a vector that contains the RV, but also some information on the star.
Oh, I see. Okay.
And that is something that perhaps with machine learning methods could tackle. How much information do you keep? You don't want necessarily an image of the star, but something that is related to the RV in a way.
Correlation.
Yeah.
That was excellent. Thank you very much. That was wonderful. Enjoy the rest of your trip.
Yes, we'll do. Thanks. Yeah, and worked out with the time. Yeah.
I think we'll still have this one until 12:30, so still.
Yeah, okay. So
Yeah, I unfortunately have the same meeting as Patrick to go to.
Good. Yeah.
But no, this is a great talk. I do more, it's weird because I do extragalactic science, but I'm doing instrumentation for this. So my brain is just all different kinds of.
Yeah, so if there are any other questions, if you don't have time now, I'm up at N526. Just stop by and you can ask questions, have a chat with a cup of coffee or whatever.
Yeah. Okay. Yes.
I'll be here for 2.5 more weeks.
Okay. Good. Thank you.
Oh, this is the last slide?
Yeah.
Okay. Let me see. There's no. Oh, people online already did. Okay. So any other questions? No, that's download.
Okay.